It'll show up on my Zoom thing, my YouTube channel later tonight. So we will get started. Got it. There we go. Okay, so someone asked for question 10, so we can do that question. But is there a particular chapter we want to start with, or which chapter? So 7, 8, or 9? 9. Okay, so let's do question 10, whichever one that one is, and then we will do chapter 9. Okay, so there's that. I think I'm good. All right, so let's do question 10. The Born-Haber cycle. Yes, the Born-Haber cycle. So, the Born-Haber cycle is a way for us to understand lattice energy, the formation of ionic compounds a little bit more clearly. And so this cycle is we're just utilizing Hess's law and us understanding, okay, if I add up all the steps to some type of process, those enthalpy values add up to one another. So what we're seeing here is the Born-Haber cycle for the formation of calcium chloride. So if this was chapter 2 and we wanted to understand, okay, what is calcium chloride made out of? What are the ions that are present in calcium chloride? We know that the cation is what charge for calcium chloride? What are the charges there? Calcium is a charge of +2. And then chloride is -1, and there's 2 of them there. And so we need to think about the steps required to make those ions from the elements in their most stable state. So there's a lot of different elements here coming together. Our understanding of, okay, well, first, what is the reaction for the formation of calcium chloride that we would look up in a table value? And so that's this first step right here. Delta H1 is describing the formation of calcium chloride. Like this could be a chapter 5 question from thermochemistry. We want to think, okay, what elements are required to make calcium chloride, 1 mole of calcium chloride? And so the reactants that you would start with would be 1 mole of calcium solid, because that's calcium in its most stable state. And then chlorine, how is chlorine found in nature? What is its most stable state? Just Cl2, yeah, so it's one of the diatomic, so Cl2, but what's the state there? Physical state, like liquid, solid, gas? It's a gas, yes. Okay, so there's some things to unpack here. So this first step is the delta H of formation. That's a chapter 5 question. And so we're thinking about, okay, how do we take these elements in their most stable state and turn them into ions? Because the thing is if we look at the reactant side, both of those reactants are neutral, like charge neutral, calcium 0, chlorine 0. But on the product side, we know that calcium is actually calcium 2+, and chloride is Cl-. So we need to think about, okay, what are the steps required to go from calcium solid to calcium 2+ in the gas phase, chlorine gas to chloride minus in the gas phase. So this is where the ideas of ionization energy come into play, electron affinity, because we need to turn this calcium atom into a calcium 2+. So if we look at all of these different steps, we already identified what that first step is, and our goal is to get the ions in their gas phase. That's our goal, because we want to relate this to lattice energy, which is this last step. So the absolute value of this very last step, this very exothermic process, is lattice energy. That's the energy we get back when we bring these ions together in their gas phase. Although lattice energy is endothermic value, it's actually the reverse of this reaction. But in Hess's law, we actually utilize the reverse reaction, and that's why this is exothermic. So lattice energy, by definition, is the energy required to separate 1 mole of the solid into its gaseous ions, so to rip it apart. So we understand that that's endothermic, that requires energy. But in this cycle, we're bringing the ions together. So our goal is to turn these neutral elements into ions in their gas phase, so then we can utilize lattice energy. So I guess the first part of this question is, okay, describe each step. What is the significance of each step? We did the first one. That's the formation reaction. That's a chapter 5 question. And now we need to think about the subsequent steps to get to the ions in their gas phase. So this second step, so delta H2, is turning a solid into a gas. So what would that be called, that energy? Turning a solid into a gas. So turning a liquid into a gas is called boiling. So turning a solid into a gas, we would call that what? Sublimation. Yeah, so this is the energy, sublimation, is the energy to sublime 1 mole of calcium solid. And that's a value you can look up. It'll be in a value as a kilojoule per mole. All right? Okay, so that's the first step, is subliming calcium to calcium gas. So then the next step, delta H3, let's think about how is this step changing. I'll highlight what changed. So this first step, we sublimed calcium. And then in the second step, we're turning chlorine gas, the diatomic, into 2 chlorine atoms. So let's think about what we did. We turned a molecule into 2 atoms. So we broke the chemical bond between there. So this step, delta H3, this is the chlorine, I guess, chlorine bond enthalpy. It's the strength of that bond, enthalpy. So this is the same value, back in chapter 5 when we talked about, okay, what's the strength of a chlorine-chlorine bond when we broke bonds and we made bonds and we calculated delta H of reactions. This is that same value. What is the energy to break that chlorine-chlorine bond? Because that's what we did in this step. All right. So now at this point, now we just have gaseous atoms, but there's a problem. They're neutral. Are these atoms, calcium and chlorine, neutral in an ionic compound? No, they're not. They're ions. So we need to turn them into ions. So the first step, the next step here is, if I highlight this, we're turning calcium gas into a calcium plus and an electron. So now finally, this is chapter 7 material. What step is that? What is that called? Taking an electron off of a calcium atom. What is that called? That's ionization energy, yeah. Specifically, the first ionization energy of calcium. Is that a value you can look up in a book? The first ionization energy of calcium? Yes, that is. Yes, so this is something that we can, again, look up in a book. Okay, so that's delta H4 is the first ionization energy of calcium. And then let's see what that next step is. It's turning calcium plus into calcium 2 plus. So now we have 2 free electrons floating around there. So this step, we're taking another electron off. So what do we call that step? I know it's called ionization energy, but specifically, which ionization energy? The second ionization energy of calcium. Yeah. Is that going to just be the same number as this first ionization energy? Do I just double this step? No, it's actually a different value because the first electron's always going to be the easiest to take off. The second one's going to get harder. Third one's going to get even harder. So you can even see that these 2 values are slightly different, that it's harder to take off that second electron. Okay, so now we have calcium 2 plus and 2 free electrons and 2 neutral chlorine atoms. So if we think about the next step, we turned calcium into the ion we want, but now we need to turn chlorine into the ion we want. So does that mean we need to ionize, we need to do ionization energies to chlorine? Is that what we want to do next? Think about what we need to produce to make an ionic compound. We have calcium, which is the cation, but chlorine in this compound, is it a cation? No, it's not. So we're not going to use ionization energy. So what property are we going to use here instead for chlorine? Not ionization energy, but electron affinity. Because electron affinity turns neutral atoms into anions, and that's what we want. So that's what this last step is the electron affinity of chlorine. That each of these chlorines are going to grab one of those electrons. And so typically, especially for nonmetals, electron affinities are exothermic processes because that electron is highly attracted to a high effective nuclear charge, that chlorine has, and so we see that this step is a downward step. And so we actually have to do it twice because we need two chlorines, we need two chloride anions. So this step, if you would look up the book value for electron affinity of chlorine, we would have to double that value to get this negative 700 kilojoules value, all right? Okay, and so after that last step, electron affinity of two chlorine atoms, so I'll just put a ×2 there because there's two chlorines there. Now we have the ions in the gas phase, and now we can bring them together to form our ionic compound, and then the very last step is lattice energy. And so Born-Haber cycles for substances, they're all going to look really similar. The first step is to turn all of the elements into gaseous atoms, and then you need to do the correct number of ionization energies and electron affinities to get the charge that you want. So we have our ions in the gas phase, and you go down. So you see, like, we needed two different ionization energies to get to calcium because calcium's a 2+ cation. But if we were just doing like a +1, -1 ionic compound, then we would only have to do one ionization energy. We don't only have to do one electron affinity to get to ions in the gas phase. All right, so those are all the steps. So now the last question is, what is the lattice energy of calcium chloride in kilojoules? So I give you all of the energies for each step, but which I didn't give you is the value for that last step, delta H7 in this case. And so in general, when looking at a Born-Haber cycle like this one, oh wait, you guys don't need to see me twice. Let me get rid of that. So for Born-Haber cycles that are given in a graphical way like this, it becomes kind of straightforward in a sense because all the values are given to you. So we just have to add those numbers as given here. So in general, how I calculate the steps in the Born-Haber cycle when given it in a graphical way like this is the delta H of formation. So I like to think of this first step as like my reference step, delta H of formation, equals all of the steps. So I'll say sum of all of the steps to get the ions in their gas phase. And then what the last step is you subtract lattice energy. All right, so in this question, and I'll highlight these, delta H1 is equal to delta H2, 3, 4, 5, and 6. But then you want to actually subtract that last step. You want to subtract lattice energy. So I'll write that down here. Delta H1 is equal to delta H2 all the way to delta H of 6 minus lattice energy, and then that's how we're going to calculate lattice energy because all the other values are given here. All right. Okay, so if we want to do that, we just put in the numbers exactly as is on this graph. So negative 795 equals positive 178 plus 242 plus 590 plus 1,145 minus 698 because that step is exothermic. You do just want to use that number as is, minus lattice energy, and that step is what we are solving for in this case. So we solve for lattice energy. There's only one variable, and this is the only question on this whole packet that requires a calculator, but I don't feel like taking it out. So if you calculate it, you get lattice energy is equal to 2,252 kilojoules for this example. And so the way that, I generalize how to put together this cycle, really it's geometry. It's just geometry. The heights of all of these upward arrows must equal the heights of all these downward arrows. So if you think of it as like a box and you were trying to figure out, okay, what's the height of that missing piece? That's what it is. But we want to report lattice energy as a positive value because of the definition of lattice energy. Okay, so someone asked, but remember, please submit questions to everyone so everyone can see it. So someone asked, why is chlorine more electronegative than carbon, but oxygen is more negative than chlorine. So that has to do with electron affinities and effective nuclear charge. So if you look at the effective nuclear charges of those atoms, chlorine is the most electronegative. It has an effective nuclear charge of +7, and so it's going to attract more electrons to one another. So effective nuclear charge trends with electronegativity in that case. Okay, so that is question 10. Goes over lattice energy, the numerical way that we calculate lattice energy. So let me do another one about lattice energy, but not as mathy. So here's another way we can ask about lattice energy. And so, what? Okay, I don't know. Okay, I don't know what raising hands means. If you have a question, just write it on the chat. So the other way we can ask about lattice energy is just a qualitative way. And so in this question, we're just asking you to order the magnitudes of lattice energies for these different compounds. And so basically lattice energy, remember, is the height of this step. We can predict qualitatively magnitudes of lattice energy based upon charges of the ionic compound that we're working with and the size of those ions. So if we look at these 4 different substances, we can order them in magnitude of lattice energy, where the first thing we want to do is look at the charges of the ions present. And so the trend is the more attracted those ions are to one another, then the larger the lattice energy will be. Because the idea is, okay, if I have a +1, -1 ionic compound, lattice energy is the energy to rip those ions apart. Versus if I have a +2 and a -2 ionic compound, lattice energy is still energy to rip those 2 things apart, but if we compare those, if you have the choice, which one's going to be harder to rip apart, a +1, -1, or a +2, -2? Which one's harder, A or B in this case? B, yeah, because the charges are higher. And so that's the strategy we want to go with here, that we want to first, when we order lattice energy magnitude, all right, lattice energy magnitude, lattice energy will increase as charges of your ions increase. When charges match, what you want to do is you want to then look at the size. So let's just order everything in terms of their charges first to get the general order of the lattice energy of these compounds. So what we want to do is just look at the charges of the ions present. So we have a +1, -1. So this is kind of, chapter 2 stuff. Magnesium is what charge in magnesium chloride? +2, -1. So I know there's 2 chlorines, but just look at the charge of one of those chlorines. Calcium sulfide. So we have calcium, which is what charge? +2. Sulfide is -2. And then sodium chloride is +1, -1. So which of these compounds is going to have the greatest lattice energy? Which one's the hardest to rip those ions apart? Calcium chloride, yes. Calcium sulfide. And then what's the second most? Magnesium chloride, yeah. All right, so if you just look at the products here, so this is +2, -2, so that's kind of like a product of 4. Here we have +2, -1, so that has a product of 2. And so the last 2 here we see are sodium iodide and sodium chloride. So those 2 have the same exact charges. So does that mean that we can't figure out which one's smallest? No. So what's the second step? What's the second thing we look at in terms of lattice energy magnitude? Size. Yeah, so we want to look at size if Q1 times Q2 match. All right, that's when we want to look at size. So let me ask you this. If we have really tiny ions that are +1, -1, and we're trying to rip those apart, think about the energy required to rip those apart. That's lattice energy. Versus if we have really big ions. which one is harder to rip apart, A or B? When the ions are really, really small, or when the ions are really, really big? What do you think's harder to rip apart? When things are small. Yeah, so when things are small, those attractions, those particles are really, really close to one another. And so if we remember potential energy, that equation, Q1 times Q2 over distance. So when the distance is small, we see that potential energy, that magnitude increases. So in option B here, it's harder to rip apart ions that are small versus when they're really large. So if we look at these two, our last two that we're trying to order here, they're both +1, -1. They both have the same charges, but their sizes do differ. So sodiums match, but the anions do not match. So that's what we want to look at. So we're comparing iodide versus chloride. So of those, which one is smaller? The smaller one is going to have the larger lattice energy. So which one? Chlorine or iodide? Or iodine? Chloride is smaller, yeah. So chloride is smaller. If we look at the periodic table, all right, that it's in a higher or like a lower N value, so there's less shells there. So we see iodine is larger than chlorine, and so that means NaI is going to have the smallest lattice energy because the ions are biggest, and then sodium chloride is going to have the slightly larger lattice energy because the ions are overall smaller. Okay. Okay, cool. All right. See how we did that? Always look at charges first, and then when the charges match, then you look at size. But when we look at size, it's the smaller size has the larger lattice energy. Okay. Okay. So a question was, what is a debye? And a debye is how we numerically calculate dipole moment. So when you do dipole moment equals Q times R, when you multiply those together with the right units, you get dipole moment, which is in the unit of debye. So things with larger dipole moments have larger debye values. Okay, so let's move on to chapter 9 because that's what was asked. So we went over lattice energy. Okay, is there a certain one in chapter 9 we want to go over? Which one? All of them? Okay, we'll just go in order then. We'll just go in order. Okay, so chapter 9. Chapter 8 and 9 definitely relate to one another because we're constantly drawing Lewis structures of things. But chapter 9, we go into more details of how do we interpret those Lewis structures? How do we get more information about a molecule given a Lewis structure? So we just went over ionic compounds, studied their lattice energy. So we looked at the bonding characteristics of ionic compounds. So now with molecular geometry and Lewis structures, we're now shifting gears to molecular compounds. So if you want to relate that to, chapter 2 when we named things, remember there were two types of ways we named things. Ionic compounds had one set of naming rules, and molecular compounds had another set of naming rules. So just like in these chapters, we looked at the bonding of ionic compounds, now we're looking at the bonding in molecular compounds. So will we ever ask you what the lattice energy of a molecule is? Will we ever ask you a lattice energy of a molecule? No, because lattice energy is related to what kind of compound? We just went over it. We always looked at charges and size. So ionic, yes. Versus now we are switching gears to molecular compounds. So this is specific to molecular compounds. Same idea. Will we ever ask you to draw a Lewis structure of an ionic compound? No, no. But we will ask you lattice energy of ionic compounds. So I want you to think about those two categories. They're separate in this case. So when you're studying, we have bonding characteristics of ionic compounds, bonding characteristics of molecular compounds. All right. So I'll answer this question as we go through this. Yeah, you don't really need to memorize the charts as long as you understand electrons. They repel one another. All right, So let's draw the Lewis structure of CF3 plus. All right, so there are 6 steps to drawing a Lewis structure, and if you memorize and do those 6 steps, you will always be right. All right, so the first step in drawing a Lewis structure is you want to count the number of valence electrons of the atoms that are present. The second step is adjust for charge if there is any charges. So in this one, CF3 plus, there is a charge, so we adjust for charge. The third step is to draw the skeleton structure. All right. I think the fourth step is we put electrons on the outer atoms and fulfill those octets. The fifth step is any leftover valence electrons we put on the central atom. And then the sixth step is we make multiple bonds if needed, All right. Okay, so let's use those 6 steps to draw CF3 plus. Okay, so first step, we count valence electrons. So carbon has how many valence electrons? How many? 4. Where did you get that? Did you memorize that? Did you memorize it? Nope. Where do we get that carbon has 4 valence electrons? On the periodic table, yes. Okay, and next we have fluorine, but specifically we have 3 fluorines. All right, so fluorine has how many valence electrons? 7, but there's 3 of them, so we want to multiply by 3. And so when we add those up, well, I don't want to add them up yet, because what you'll get is an odd number. So what we want to actually do is adjust for charge. So this is a cation. So in order to make a cation, how do you have to adjust electrons? Do you add more electrons or you take off electrons? Take them off. So we want to subtract 1 electron because it's a cation. Yes, it's positively charged, but to get that, we have to remove an electron. So we have how many electrons to spend? 24. All right, and so we need to make sure that our structure has 24 electrons drawn and nothing more. All right, so we did steps 1 and 2, counted valence electrons and adjust for charge. So 24 electrons, that's how much money we're allowed to spend in drawing the structure. So we need to make sure that we don't overspend or underspend. So we draw our skeleton structure. So that typically means determining what the central atom is. Usually, like 95% of the time, the central atom is whatever element is written first. So in this case, it's carbon. And so we want to draw carbon with 3 fluorines around it. All right? But the actual way we determine what the central atom is, it's actually the most electropositive atom is always the central atom. But usually, it's written first in the formula. All right, so that's my skeleton structure. But to draw this skeleton structure, I drew single bonds to the central atom to the outer atoms. How many electrons did I spend so far? 6. Yes, I know I drew lines, but each of those lines represent 2 electrons. So I've already spent 6 electrons. So we need to keep that in mind. We've spent 6, but we have 24 to spend. So that is step 3. We drew the skeleton structure and used up 6 of our electrons. Now we want to fulfill octets of our outer atoms first, keeping in mind that we already spent 6. So let's complete the octets of the outer fluorines. So 6 electrons, 7, 8, 9, 10, 11, 12. That fluorine's done. So 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I'm done. All right. So this is the Lewis structure of CF3. So you might notice, I actually regret picking this molecule. So I regret it because all of these fluorines have fulfilled octets, but the central carbon does not, and that's okay in this case. So you might want to try to make a double bond here, but we actually don't want to do that because it messes up formal charges. So this is the Lewis structure of CF3+. All right, because we spent all of our electrons. Okay, so there we go. That's the molecule we want to look at. So what is the electron geometry around this central atom? So electron geometries, we want to think about what is the number of electron domains about that central atom. And so when we look at this, when we calculate electron domain geometry, we want to consider all of the electrons that are in lone pairs and bonds. Because these bonds, they have electrons in them, right? If we had a lone pair present, those are also electrons. And so the big idea of Vesper theory, because after doing the Lewis structure, we want to think about Vesper theory, is that electrons repel one another. They want to repel one another because they're all negatively charged. And so when those electrons repel one another, that's the geometry that it takes on. So if we look at this molecule, it has 3 electron domains because there's 3 bonds present. And so if we think about, okay, if 3 repelling domains repel one another, how can we maximize, or I guess minimize repulsions so the electrons don't bump uglies with one another? And so to do that, 3 electron domains will spread out all 120 degrees away from one another. And we call that what shape? Trigonal planar. Yes, trigonal planar. All right? And so since we got the 3 electron domains, we got trigonal planar. They'll all spread out. So how we get molecular geometry is we just want to consider lone pairs, right? So if there's any lone pairs on your central atom, can you see lone pairs? No. But can you see bonds? Or I guess, can you see other atoms? Yes, you can. So when we think about molecular geometry, we want to ignore lone pairs in your electron geometry structure. So I don't like this example because we don't have any lone pairs present. So since there are no lone pairs, this is also trigonal planar because that means we can see every single electron domain. But if we had a molecule that looked like this, like A, and then like 2 bonds that look like that, does this A atom, how many electron domains are around that A atom? 1, 2, 3. So the electron geometry would be trigonal planar again, but one of those domains is a lone pair, and we actually can't see it. So what we would do here is recognize, oh, there's one lone pair. We can't see it, so we just erase one of the legs that are there. All right, and so we would see in this molecule, this would be bent because that lone pair is still there. It's still repelling the bonds, but we can't see it. All right, and so this molecule would be bent, but you might be thinking, but I drew it linear. Lewis structures don't have to represent what it actually looks like. Okay, so question says, why do these compounds with overall charges violate the octet rule? Carbon with 3 bonds, sulfur with 4, so I mentioned that CF3, I actually don't like this example because it violates the octet rule. So we really shouldn't be doing this example. An example like this because there are sometimes the octet rule is violated. And so examples are for beryllium, boron, and for expanded octets that include sulfur and phosphorus sometimes. And so this example, I should not have included it. So maybe we should just do a different example. Why don't we do, well, I guess before we're done, let's just finish this one with our Vesper theory, and then I'll pick a different molecule and we'll answer the same questions. Okay, so we got the molecular geometry, we got the electron geometry, so let's predict the bond angles in this molecule, so CF3. So what would the bond angles be? This is directly related to those geometries that we just got. Yeah. What do we think? The bond angles. Okay, 120. How did we get 120? Your brain, yes. Also that we recognize that it was trigonal planar, right? It's trigonal planar, so 120 would be those bond angles. Do you think it would be exactly 120 or just around 120? What do you think? Exactly 120? Yeah, in this example, it's going to be exactly 120 because all of those bonds are identical. And so there are examples where it's not exactly 120, and I'll do an example for the next one where it's not exactly 120. Okay, So let's just keep going. What is the hybridization of that central atom, according to valence bond theory? What do we think? sp2. So how do we get that? So hybridization of the central atom, the big idea here is the number of electron domains that we use to get the geometry is equal to the number of atomic orbitals we need to hybridize. So in this case, there's 3 electron domains, so we want to combine 3 different atomic orbitals to hybridize that central atom. So it means an s orbital and 2 p orbitals. So that's why we say sp2. All right, there's 3 electron domains about that central atom. Okay, and then finally, is this molecule polar or nonpolar? So we want to think about the geometry of the molecule, and we want to think about the bond dipoles or any polar bonds that are present in this molecule. So if we look here, there are 3 different polar bonds in this molecule. I know that they're polar because carbon's not very electronegative, fluorine is very electronegative. And so all of these bonds create this polar bond, but we need to think about how those bonds are oriented in 3 dimensions. And so we already said all those bonds are 120 degrees from one another. So if we think about those bonds as vectors, since they're all 120 degrees, they all cancel out with one another. And that was said on the chat, very good. So this molecule would be nonpolar. But what if I changed one of these fluorines for a chlorine? Would it still be nonpolar? No, in this case it would be polar. It doesn't matter that we calculate how the vectors cancel. We just need to see that, oh, okay, when we look at this molecule, sorry, there's a bunch of stuff. What was I saying? Oh yeah, once it was a chlorine, then we just need to understand, oh, those bond dipoles aren't all the same value, and so we will get a, when they do cancel, we'll still have an overall non-zero vector at the very end, that this arrow, if I draw those bond dipoles, like this one's going to be a smaller arrow, these ones will be bigger, and so those vectors don't exactly cancel. And so when they don't exactly cancel, then we can say the molecule is overall polar, right? Just when they don't cancel. Okay, will a double bond affect polarity? Sometimes. And I'll show you an example. Okay, oh, there's one more. According to valence bond theory, what 2 orbitals are involved in the CF bond in this molecule? All right, so the last question here is us thinking about, okay, this bond in CF3, so if we go back here, that's a fluorine. We want to think, okay, what orbitals are overlapping? Okay, there's a lot of arrows going around here. We want to think about what kind of orbitals are these 2 electrons in a carbon-fluorine bond that overlap in space to make that chemical bond. So with Lewis structures, when we did the 6 steps, we just considered those electrons to be dots on a page, and we say, oh, 2 dots make a chemical bond. But in valence bond theory, we understand that, oh, chemical bonds are only made when orbitals overlap. And so we already determined that this carbon is sp2 hybridized. So that hybridized orbital is the orbital that one of those electrons are in. And so now we need to ask ourselves, where's that unpaired electron on fluorine overlapping with carbon? And so fluorine, its unpaired electron, if we write out the electron configuration of fluorine, it's 2s2, 2p5. And so, if you draw that out, we can clearly see where that unpaired electron is, what its shape is, because valence bond theory says orbitals, unpaired electrons have to overlap in space. One of the electrons is in an sp2 hybrid orbital on carbon, but on fluorine, it's in what kind of orbital? Where's that unpaired electron? It's in a p orbital. Yeah, so can a p orbital overlap with a hybridized orbital to make a sigma bond and head-on overlap? Yeah, so that's where fluorine's unpaired electron is. So this answer would be carbon's sp2 hybrid orbital and fluorine's 2p orbital. Those 2 are overlapping in space. I can kind of draw what that looks like. So there's one of the sp2 hybrids. there's fluorine, and so those two orbitals are overlapping in this way, where those unpaired electrons are overlapping in space to make that chemical bond. All right. Okay, so let's just do another example that's not CF3+, because it violates the octet rule. I don't know why I chose that one. Let's do a different one. Let's draw the Lewis structure of H2O. All right, so 6 steps. How many electrons come from carbon? 4. Then we have 2 hydrogens, so then we add 2 times 1, and then oxygen has 6. Great, so if we add that up, we have 12 electrons to play around with. This is a neutral molecule, so we don't have to adjust for charge. 12 is the number that we get. Okay, so what is our central atom? What's our central atom? It's going to be carbon, yeah. So there's a couple reasons. It's written first. Also, it's the most electropositive atom because oxygens are only other option, but carbon's more electropositive or less electronegative than oxygen. Can hydrogen ever be a central atom? No, because it can only ever make one bond, so hydrogen will never be a central atom. Okay, so there's carbon. We draw our skeleton structure, so we have 2 hydrogens and an oxygen there. All right, how many electrons have I drawn so far? 6. So we have 6 more to place. So now we want to place electrons on the outer atoms first, fulfilling octets. Do I need to put any electrons on hydrogen? No, they're done. They have fulfilled octets already because hydrogen, I guess, is an exception. It only needs 2 electrons because it only has a 1s shell to fill. So that means our leftover electrons are going to go on oxygen. So there we go. All right, so I spent all my electrons. But if you look here, hydrogens have fulfilled octets. That oxygen has a fulfilled octet, but carbon does not. So does that mean, can I just draw 2 more electrons to fulfill carbon's octet? No. Yes, that fulfills carbon's octet, but did I have those extra electrons to spend? No. So what I actually want to do is step number 6, which I erased, is make multiple bonds in order to fulfill carbon's octet. So all we're doing is moving electrons that we already have on the structure to donate into carbon so it can fulfill its octet. So I'm going to take one of the lone pairs on oxygen and turn it into a multiple bond, so then that carbon can share some of those electrons. So then the full Lewis structure here is going to be carbon with a double bond to oxygen. Oxygen still has 2 lone pairs present, and then that carbon has the 2 hydrogens there. So if you look at the Lewis structure, there's still 12 electrons there. That's how much I could spend. But there's a double bond to oxygen and carbon, so we can complete that octet that's there. All right, so there's our Lewis structure. So let's go through all the same questions. What is the electron geometry around that carbon? How many electron domains are there? 3, yeah, so that double bond counts as 1 domain. So it's just electrons in bonds or in lone pairs, they all repel one another to get your electron domain geometry. So since there's 3 electron domains, this is still trigonal planar. Are there any lone pairs for us to worry about? No. So since there is 0 lone pairs present, it's still going to be trigonal planar. Planar. All right, because since there's no lone pairs, there's nothing to cover up. Okay. What are the predicted bond angles? So what is this bond angle, the green one, and the pink one? What do you think? Are they going to be exactly 120? Because we're still doing trigonal planar, so it's 120. Yeah, so no, it's not going to be exactly 120. 120 is our ideal bond angle. So does that mean since I drew it this way, this green angle, is that 180 then? No, just because I drew the Lewis structure 180 degrees doesn't mean it is. What would be better is if we drew it closer to what a trigonal planar looks like. So it's going to look like this. all right? So in our previous example, CF3 plus, all the bonds were identical. All the electrons were in bonds were identical, so they repelled one another equally. But in this example, you know, the electrons are still repelling one another. But if you think of, okay, what takes up more space, a single bond or a double bond? Think about how many electrons are in each of them. A single bond is made of how many electrons? 2. But a double bond is made up of 4 electrons. So I just like to think of, oh, that double bond just takes up more room. Takes up more room. So what is it going to do to this green bond angle right here? It's going to close it up. So that green bond angle is going to be a number slightly less than 120 degrees. Slightly less. And then if we compare this bond angle right here between the oxygen and hydrogen, it's going to be what? How is it going to deviate away from 120? Less than? More than, yeah, because the double bond takes up more room, all right? It's just, I like to say it's fat and juicy and takes up more room. And so you'll see a bond angle greater than 120 degrees, all right? It takes up more room, so it's going to squeeze this hydrogen-carbon-hydrogen bond a little bit closer because the double bond is just taking up much, much more room, right? Same thing if we had a bond angle that looked like, if we had something that looked like this, all right? And we had a lone pair with 2 bonds, this would also be trigonal planar. Okay, maybe I shouldn't draw it that way. I'll actually draw it so it's kind of trigonal planar, all right? So lone pairs also take up more room. So that lone pair is taking up more room. It's going to push these bonds closer together. So what will this bond angle be? Exactly 120, more than 120, or less than 120? Less than 120, yes. Yes, less than 120. Because that lone pair is just taking up more room. A double bond also takes up more room. Okay, so let's finish this up. What is the hybridization of that central atom? sp2. Yes, 3 electron domains, it's sp2 hybridized. Is this molecule polar or nonpolar? Polar, yes, because in this case, it's, you know, trigonal planar, but the atoms that are attached to it, they all have different bond polarities. And so we know that that won't cancel out. It doesn't matter what it cancels out to, we just know it doesn't cancel out to 0. Yeah. I look at that carbon, and I count how many electron domains there are, and that's how many atomic orbitals you combine. That's it. Yeah. So we got that there are 3 electron domains. So you combine an S, a P, and another P. If there were 4 electron domains, we would combine an S, a P, another P, and another P. So we would call that what hybridization with 4 electron domains? sp3, yeah. So that's it. All right, sp2, okay, and then finally, polar, nonpolar, using valence bond theory. So instead of the carbon fluorine, let me ask you, what 2 orbitals are involved in the carbon-hydrogen bond? The carbon-hydrogen bond, so this bond right here. Where do each of those electrons, those unpaired electrons, what kind of orbitals do they come from? And then the question is, they have to overlap in space to make a chemical bond. So carbon's unpaired electron is in what kind of orbital? sp2, we already got it. Yeah, sp2, because we already got its hybridization. But where is hydrogen's unpaired electron? Is it also in a p orbital, just like in that fluorine example? No, it's in what kind of orbital? A 1s. Yeah, hydrogen only has 1 electron, and it's in a 1s orbital. And so we can draw the same picture here and make sure that it can produce a sigma bond. So an sp hybrid orbital looks like that. So that's carbon, one of carbon's sp2 hybrid orbitals. An s orbital looks like this. Right, there's s, that's sp2. Can these overlap to make a sigma bond? Is that a sigma bond right there? Yes, it is. So that's the 2 types of the 2 orbitals that overlap in space to make that chemical bond. When you write out bond angles, do you have to label which bonds are which? or can you leave it in the drawing? So, Misha, on the exam, we make it very clear which bond angle we're talking about. So I made them different colors because they are different bond angles, and I want to distinguish that this pink angle is different from this green angle. So like on an exam, we could specifically say, okay, what is the bond angle of the pink one? And you would have to say more than 120 degrees. Okay, and so the second question here is, why is it polar? Because, so in the other example, we had carbon with 3 fluorines, but all the fluorines have the exact same bond polarity. So we have the same vectors canceling each other out in 120 degrees from one another. But in this example, you can say they're still about 120 degrees away from one another, but this oxygen has a different electronegativity than these 2 hydrogens. Yeah. It's not necessarily because of the double bond. What 2 orbitals would it be for carbon? That's a little bit different. I'll talk about that a little bit later. In this example, it's not a good time to go over the orbitals for carbon and oxygen. Okay. So if you're combining, is it always sp2? Yes, it is. Okay. I think there was one more question I wanted to ask. Oh, people keep asking me, if there's double bonds, is it always polar? No, it's not. So let's do an example with nitrate. Let's draw the Lewis structure for nitrate. So we got a nitrogen, so 5. 3 oxygens, so 3 times 6. It's an anion, so do we add an electron or remove an electron? Add one. Okay, so that adds up to 24 valence electrons. So we draw a nitrogen and 3 oxygens. So that's 6 electrons so far. So I fulfill the octets of the outer atom. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, I'm all done. So all the oxygens have fulfilled octets, but does that nitrogen have a fulfilled octet? No. So what should we do? Should I just draw 2 more electrons? Nope, can't do that. I don't have any more electrons to spend. So what I'm going to do is move one of the lone pairs on the oxygens to make a double bond. But the question is, from which oxygen do I move to make a double bond? Do I make the double bond here? Or do I make it there? Or do I make it there? Does it matter? No, it doesn't matter. Why is nitrate interesting here? There's more than one way to fulfill the octet. There's more than one oxygen that can fulfill the octet. So in what we see actually in real life is that all of the oxygens do. So, we can complete the Lewis structure. I'm just going to put the double bond on the top. All right. So, we've finished the octet. It looks like this. All right. So everything now has a complete octet. This is what nitrate looks like. I put the double bond up here, but does that mean that nitrate has 1 short bond and 2 long bonds? No. So nitrate actually undergoes resonance. That double bond actually exists in all 3 locations at the same time. If we were to look at a nitrate molecule and measure its bond lengths, we would see 3 bond lengths that are all the same size. How I like to think of it is that this double bond is smeared across the entire molecule instead of being localized in one spot. Yeah. SF3, or so I mentioned that was a bad example. Can we just let's forget about CF3 plus. It's an exception to the octet rule that we never talked about in class. All right? Yeah, don't worry about it. Okay. So in this one, yes, we want to make a double bond. All right. The real reason is because of formal charges. So in this example, we do not see a short bond and 2 long bonds. Right? So we actually see a bond order. We don't have a molecule that has a bond order of, a short bond and 2 long bonds. So we don't see bond orders of 2 and 1. We actually see a bond order that's a weighted average of all of the bonds because they're identical. So the bond order in this molecule, I like to think of, okay, there's a double bond, 2 single bonds. We have to do like a weighted average of all of them. So it's a bond order of 4/3. So the bond order in this molecule is actually 1.33. All right, that it's a little bit, all the nitrogen-oxygen bonds are a little bit stronger than a single bond, but not as strong as a double bond. Okay, so with all of those things together, what do you think the bond angle is in this oxygen-nitrogen-oxygen bond? What do we think it is? Is it less than 120 degrees? No, it's not. They're all exactly 120 degrees, because I asked you, does that double bond actually exist there? No, the double bond exists in every single location, but I have to just draw one of the resonance structures. So yes, there's a double bond here. You would think, you know, that double bond takes up more room, but that double bond actually doesn't exist there. It's in all 3 locations. That the bond order in the nitrogen-oxygen bond order in this molecule is actually 1.33. It's not a double bond and 2 single bonds. And it's due to resonance, right? So resonance affects bond orders, it affects bond strength, it affects bond length, and it affects bond angles. So this bond angle is actually exactly 120 degrees because that double bond doesn't actually exist there. But if we were looking at like our other molecule, right, where we had carbon, oxygen, and 2 hydrogens. Can that molecule do resonance? Can formaldehyde, so carbon, the one that we just did, can this do resonance? Is there more than one way we can finish the Lewis structure? No, that double bond has to live there. So does this bond angle, is this bond angle exactly 120 degrees? No, it's not, because in this example, that double bond does affect the other bond angles. But in this example, that double bond does not actually live there. So the bond angles are all exactly the same. Just like all the bond lengths are the same, bond orders are the same. Yeah, okay, question. Oh, you want to do formal charges? Yes, okay, this one right here, yeah. All right, are we good with that? Okay. I mean, I could spend the entire hour on this, so but we only have an hour left, so let's just move on to formal charges. Yes. So, which of the following molecules is the most dominant structure according to formal charges? So, let's go over how to calculate formal charge first. So we need to calculate the formal charge of each atom given a Lewis structure. So the trick I use to calculate formal charge is I want to think about how many electrons does an atom want, and I subtract how many electrons it has in the Lewis structure that's drawn. Want, so that number want comes from your periodic table. So it's basically the number of valence electrons for that specific atom. So for nitrogen, how many valence electrons does nitrogen want in terms of its number of valence electrons? 5, yes. So wants minus has. So nitrogen wants 5. How many electrons does oxygen want? 6. And so it's going to be 5, 5, 6 across the entire, all 3 structures, right? Has is a little bit different, and I want to separate this. This is different. Calculating formal charge is not the same as octet. So throw that out the window right now. We're not calculating octet, right? Because if you actually look at all of these atoms, are there any atoms with incomplete octets? Nope, every single atom has a complete octet technically. They all have 8 electrons somehow being shared with it. So formal charge is not the same as octet, right? So what we want to do for has is we want to only count half of the bonding electrons, but you want to count all of the lone pairs. So that's how we calculate has. So this is what I do. So if we look at one Lewis structure, each of those bonds has 2 electrons in it. So I like to think, okay, each bond, we're putting the electrons back on each atom. So this single bond has 1 electron with that nitrogen. This other electron goes with that nitrogen. But a triple bond is made up of 6 electrons. So 3 of the electrons are going to go on that nitrogen. The other 3 are going to go on that oxygen. So when we calculate the has line, what we want to do is, again, count half of the electrons that come from bonds, but all of the electrons as lone pairs. So how many electrons are boxed in that box for this nitrogen? 7, because we have 6 lone pair electrons and then 1 electron coming from a bond, so it's -7. But then if I box this nitrogen, how many electrons are in that box? 4. And then how many electrons are on that oxygen? 5, -5. So again, 2 from the lone pair, 3 by taking half of the bonds from, or half of the electrons from the triple bond. So that's what once minus has comes from, right? So has, again, meaning in the Lewis structure, because what we're going to see is that all these Lewis structures have different has lines here. And so when you subtract these, you get, what, -2, +1, +1, all right? Those are our formal charges. So when trying to find the most correct Lewis structure, what we want to do is first minimize formal charges, where 0 is the preferred formal charge. But sometimes we have to have a formal charge on a molecule because sometimes there's a charge on the atom or a charge on the entire particle. So there has to be at least one non-zero formal charge. But if you do have a formal charge, typically what you want to do is put any negative formal charge on the most electronegative atom. Right? Those are the things that you want to maximize in terms of formal charges. Right? Where the first one is most important. You want 0 formal charges. That is the most preferred thing. Right? So those are the formal charges for the first molecule. So let's just do all of them. Once we get all of them, we'll see, okay, which one maximizes our criteria here. All right, so let's do once minus has. So once, again, just comes from the periodic table. Nitrogen typically has 5 valence electrons. Oxygen has 6. How many electrons are assigned to this nitrogen atom? 6, yes, again, because we want to split those electrons in half that have in that chemical bond, so that nitrogen has 6. How about the middle nitrogen? 4, -4. And then the last oxygen? 6, yes, so there's 6. All right, and so you add those up, and so you get +1, no, -1, +1, 0. All right, so it looks like we're getting better, right? Because we've made the formal charges smaller. We have a 0 now, but let's look at the last one and see what happens. All right, so this last one, we got the once line is nitrogen, once 5, 5, 6, but the leftmost nitrogen has how many electrons? -5. The middle one has 4, so -4, and then that last oxygen is 4? 7, yes, 1 electron from the bond, 6 from the lone pairs. And so if you add those lines up, we get 0, +1, and -1. Okay, so which Lewis structure can we just eliminate right off the bat? The first one. Why is this first one not correct? Yeah, there's a bunch of formal charges, all right? What's preferred is 0. So in this molecule, there are no zeros, so this one is eliminated, right? That the molecule is never going to adopt that Lewis structure. But then we have these last two, all right? Can we distinguish between these last two just based on criteria 1, minimize formal charges where 0 is preferred? No, because both of them, they both have formal charges present, and they both have a +1 and a -1. So it looks like we can't get around that. We can't make a Lewis structure that has them all be 0, unfortunately. So we have to choose from one of these, right? So that's where we go to the second criteria. put negative formal charges on the most electronegative atoms. So if we look at the difference between the second and third molecule, we have a choice. We can put the negative formal charge on a nitrogen, or we can put the negative formal charge on an oxygen. So which one do you think we want to put it on? We have a choice. We probably want to put it on oxygen, yes, because oxygen is more electronegative. Oxygen, if you look where it is on the periodic table, it has a higher effective nuclear charge. It attracts electrons to it more. So that negative formal charge is going to prefer itself on that oxygen. So that is the most dominant Lewis structure, where the negative formal charge is on the most electronegative atom. Okay. All right, so that's 17. So someone asked me, let's do 15. Yeah, let's do 15. Okay, let's order these substances in order of increasing bond enthalpy. So we have to draw the Lewis structures. All right, so we need to draw the Lewis structures. So bond enthalpy means strength. So what do you think, after we draw the Lewis structures, what do you think, what kind of information do we need to get from the Lewis structures? We probably need to look at bond order in this case, yes. So if we look at the bond order, recognize, oh, as bond order increases, strength increases. So unfortunately, we have to draw the Lewis structures and probably consider resonance if there is any. All right, so let's kind of do this all at the same time. Let's count valence electrons. We need to draw 3 structures, unfortunately. So SO2 has, I think, 18 we can spend. SO3, 2 minus, add 2 electrons to the valence electron count. So I think it's 26. And then sulfate has 32. All right, so let's do SO2 first. So we got sulfur in the middle, 2 oxygens. So that's 4 electrons. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the last 2 electrons go where? On sulfur. Yep, there we go. Okay, so what's the problem? Is this Lewis structure done? Nope. So sulfur does not have a complete octet. So what should we do? Yep, put a lone pair on one of the adjacent oxygens to make a double bond with sulfur. So if we draw the new structure, it'll look like this. Sulfur, a single bond, oxygen. There we go. All right, so what's special about sulfur? What's special about sulfur? It can have an expanded octet, yeah. So there's actually an additional problem to this structure, and I'll show you. Let's review formal charges again. Let's calculate the formal charges of all these atoms. Oxygen typically wants 6 electrons. In this structure, how many electrons does that oxygen have? 1, 2, 3, 4, 5, 6. So 6 minus 6. So that oxygen has a 0 formal charge. Is that good? Yeah, that's good. But now let's look at the sulfur. Sulfur typically has how many valence electrons? 6. But how many electrons are on that assigned to that sulfur? Only 5. So the formal charge on that sulfur is +1. Is that good? No, that's not preferred. And then what is the formal charge of that last oxygen? So oxygen typically wants 6, but how many are on that atom? 7. So that oxygen actually has a negative formal charge, -1. So although the sulfur has a fulfilled octet, because the formal charges aren't maximized or, minimized here, what we're going to actually see is that this oxygen will also donate electrons to the sulfur atom, so then everything has a 0 formal charge. So the actual Lewis structure of SO2 is sulfur with 2 double bonds. All right? Because if we go through formal charges, all of the atoms in this molecule with 2 double bonds, they actually all have 0 formal charges, and that's good. Yes, sulfur has an expanded octet, but that's okay because sulfur is allowed to have an expanded octet. All right, so this is the Lewis structure for SO2. Right, so there's that one. So let's do SO3 2 minus. All right, so let's keep going. So sulfur's in the middle, 3 oxygens, boop, boop, boop. So 6 electrons, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that means the last electrons go in the middle there. Okay, so if we look at this, does everything have a satisfied octet? Yes, but do you think we're done? Nope, we're not. Because what is the formal charge of that central sulfur? +1. Yeah, is that preferred? Is that good? No, that's not good. Sulfur wants to have a formal charge of 0. So what we're actually going to do is make a single bond, or sorry, turn a single bond into a double bond in this case. All right, and so when we do that, we get sulfur with 1 single bond, or sorry, 2 single bonds, 1 double bond, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then that lone pair is still there. Yeah. And so now if you look at this red molecule where sulfur has a double bond, that sulfur now has what formal charge with 1 double bond to it? It's 0 now. And so that is preferred. So here is your Lewis structure for SO3 2 minus. Or 2 minus. 2 minus. There, where it has 1 double bond, and so that's how we get that 0 formal charge on sulfur. In this example, sulfur has an expanded octet, but that's okay. Sulfur can have an expanded octet. All right, so let's do the last one, SO4 2 minus. So I know we're nowhere near the correct answer yet. We have to draw the Lewis structures first. So that's 8 electrons. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So 32 electrons. I've run out of electrons. So this time no electrons are going to go on that central atom. Okay, so sulfur right now has a complete octet. But what is its formal charge right now? It's +2. So how many double bonds do you think I'm going to form? 2 of them. Yes, I'm going to form 2 of them. So if I form 2 of them, these electrons come down and these electrons come down. I'm just picking random ones because, again, the double bonds can be formed from any of those oxygens. And same thing for this example, too. I just did it from the top, but could you have made a double bond on this oxygen? Yes, or on this oxygen. And so same thing here. I just need to form 2 double bonds, but they can come from anywhere. And so when I do that, the resulting molecule is going to look like this, where now that central sulfur has a formal charge of 0, and that is preferred. 2, 3, 4, 5, 6, and then this one has 2. And that's a total -2 charge. Okay, great. So these are the molecules we want to compare. SO4 2 minus, SO3 2 minus, and SO2. So now we need to calculate bond order to actually answer the question. We have the Lewis structures. That was the hardest part. But now let's look at bond order. To make this, honestly, to make this an exam question, worthy question, we would give you the structures because we understand that this is very time consuming to draw these Lewis structures. So let's pretend like an exam question was, oh, I give you these structures. Tell me, order these in increasing bond enthalpy. So at this point, we should just be able to look at the structures and recognize, okay, which one has the strongest SO bond, which one's the weakest SO bond. So really, we need to calculate bond order. So in this molecule, what is the bond order between sulfur and oxygen? It is 2. Yes, it is 2. Because both of these are double bonds. A double bond has a bond order of 2. A single bond has a bond order of 1. A triple bond has a bond order of 3. Yes. Both of these SO bonds, double bonds, they're identical. So this has a bond order of 2. Okay, let's move on. Let's look at this molecule. What is the bond order here? What's special about this molecule? It can do resonance. Yes, does that double bond exist only in one place? No. This molecule does not have 2 long bonds and 1 short bond. It actually has that double bond smeared across the entire molecule itself. So I recognize that this double bond can go here, here, or here. It doesn't matter. So to calculate bond order, how I calculate it, so the question is, do you recommend checking formal charge for every structure? I mean, if you have time, you should, because Lewis structure should minimize formal charges, but it's especially important with anything that can expand its octet. That's where it's really important, like in these examples. Like if carbon was our essential atom, you don't need to check formal charges. As long as carbon has 4 bonds to it, you know that that's preferred there. So especially when there's atoms period 3 or heavier. Okay, so in this example, is the bond order 2? Is the bond order 1? No, it's somewhere in between. So we calculate basically the weighted average here. So I like to just count how many total bonds there are. So there's 1, 2, 3, 4 bonds rotating themselves over 3 different positions. So the bond order is 4 over 3. So it's equal to 1.33. Right? So with that same idea in mind, what is the bond order in this one? Can the double bond, is the double bonds only in these 2 top and bottom positions? No, they can be in any of the positions. So we're not going to see a bond order of 1. We're not going to see a bond order of 2. We're going to see a bond order somewhere in between. But now the trick is, okay, well, how do I calculate the actual bond order for this Lewis structure? I like to think how many bonds are swapping places over the number of positions that there are. So there's 1, 2, 3, 4, 5, 6 different bonds swapping over how many positions? 4. So the bond order for SO in this example is 1.5. All right, and so now at this point, now that we have bond order, now we can actually answer the question and order them in increasing strength. So which bond is the strongest? SO2, and then the weakest is SO3 2 minus. Yeah, so this is the strongest, and then this one is the weakest. Perfect. So you got to consider resonance. Consider resonance. Okay. Let me do one more, but I will give you the Lewis structures right now. So let me just add a page real quick. Okay, I'm going to give you the Lewis structures, and you tell me which ones have the strongest bonds. Okay. Okay, so there's that. This is 2 minus, and so A, B, C, okay, so I want you to tell me which molecule has the strongest CO bond in it. A, B, or C? Which one? A, yeah, so let's just go through the bond orders of all of them. So the bond order in CO, carbon monoxide, what is that bond order for the CO bond? There really is only one bond, but here, this is a bond order of 3, because it's a triple bond. Yeah. Then let's look at this molecule. What is the bond order of CO in molecule C? 2. Do I have resonance to worry about there? No, it's just 2 double bonds. So it has a bond order of 2. Both of those bonds are identical. But what about B? What is the bond order there? Somewhere between 1 and 2. But what is the actual bond order? 4/3, yeah. So the bond order here is 4 different bonds swapping 3 different locations. There's a single bond, another single bond, and a double bond. 4 bonds swapping over 3 locations, so the bond order is 1.33. So the strongest bond is carbon monoxide. The weakest one is this one, carbonate. Okay, so let me swap out number 1. Okay, let's compare this carbonate with another one. Okay, which one has the stronger CO bond, A or B? The stronger bond. So let's calculate bond order again. Let's calculate bond order. So what did we say the bond order of B was? What did we say it was? 4/3, yeah, 4/3, 1.33. What is the bond order in molecule A? Again, just focus on the CO bond. What is it in molecule A? So let's think about it this way. When do we consider resonance? When there's more than one way to finish a Lewis structure. Because the idea is, I know that this double bond doesn't exist in this location because I could have put the double bond here. I could have put the double bond here. So really, the double bond exists over all 3 locations. Can we say the same thing about this molecule? The double bond can exist up here. Is there anywhere else that double bond could have been? Yeah, right here. So does that mean the double bond could also be right here? No. What's the problem with putting the double bond right here? That's a hydrogen. That hydrogen's already set. It already has a fulfilled octet. So this bond does not participate in resonance. So this molecule actually has a different bond order. So let's calculate it. So the double bond can exist in how many different locations? 2. So the bond order here is going to be a double bond and a single bond swapping places. So that's 3/2 equals 1.5. So which one has the stronger CO bond, A or B? A. And that's a much better question. Like on an exam, we would give you the 2 structures and then ask. Because we already did the hard part for you is drawing the structures, but it's up to you to recognize, oh, but there's resonance is involved here. There's more than one way to finish the Lewis structure. I could have put the double bond up top, but I could also put it down here, and it's a completely valid Lewis structure. If you calculate formal charges, you would see that they're all identical. Okay, so we have 35 minutes. So let's stop doing that. Let's do a different one. What is this? Number 24. Let's not do that one yet. Let's do, did I have one with bond angles in it? Okay, let's do this one. Let's do 20. Let's look at this molecule. Let's predict the bond angles and stuff, because we were just talking about bond angles, geometries and stuff. All right, so what's the hybridizations of the carbons left to right? So to get hybridization, we just do what? Count what? Electron domains, yes, and that number will tell us how many atomic orbitals we need to mix. So this carbon, the first one on the left, has 3 electron domains. So what is its hybridization? sp2. The middle carbon has how many electron domains? 2. So it is what hybridization? sp. That's it. Okay, and the last carbon has 3 electron domains, so it is what hybridization? sp2. Fantastic. Okay, let's order those bond angles. So remember, each of these hybridizations, the number of electron domains, remember, tells us a shape back from Vesper theory. So if we go back here, so number of electron domains is related to hybridization. So 3 electron domains is sp2 hybrid. Vesper theory says 3 electron domains is what shape? Trigonal planar. And this is useful for us to predict bond angles as well, because all of these ideas overlap with one another. SP, we said that that was 2 electron domains. What did Vesper theory say? 2 electron domains. What shape is that? 2 electron domains spread out as far away from one another. To minimize repulsions, we'll take on what shape? Linear. Yes, linear. Perfect. And then sp2, again, that's trigonal planar. So with those shapes, we should be able to get the ideal bond angle. But what do we have here that's going to screw us up a little bit? Our ideal bond angles. Are we going to actually get exact ideal bond angles here? No. It's going to deviate a little bit. So what we would see here is that, you know, bonds 1 and 3 should be around 120 degrees. Bond 2 is going to be 180 degrees because this is linear, but let's now consider double bonds and stuff. So, all right, let's look at bond angle 2. What do we think that bond angle is going to be? 180. Is it going to be exactly 180 or a little bit off? It's going to be what? Exactly. Yeah, it's going to be exactly here because, well, you might be thinking, but there's double bonds. But look, there's a double bond here. And doesn't that like kind of push the other side a little bit? But there's a double bond over here as well. So you can see that the like deviations kind of cancel each other out. You have 2 double bonds, they're exactly the same. So bond number 2 is going to be exactly 180. But will bonds 1 and 3 be exactly 120? No, they won't. Because of the unequal double bonds that are present. So let's look at bond 1. There's that double bond there. So bond number 1, is it going to be what? Greater, less, exactly 120? What do we think? It's going to be slightly less. How do I write that? Like this? Slightly less than 120 degrees. And then that means bond number 3 will be what? Slightly more than 120. And see, again, I'm being very deliberate of showing what bond angle. It's just not any, you know, carbon, hydrogen, carbon, or like any bond around that carbon atom. We're very specific about which one. And so then I think if we ordered this, 2 is obviously going to be the greatest because it's linear, but then it's going to be what? Bond angle 3? Yes, bond angle 3 and then bond angle 1. Right? If you didn't consider slight deviations about double bonds and stuff, you might try to say, oh, 1 is exactly the same as bond angle 3, but it's not, because they're in different positions relative to where the double bond is. All right, you might try to say, oh, bond angle 1 is the exact as bond angle 3. All right, you might want to try to say that, but in this case, if we consider deviations, we can, in fact, get that 3 is greater than 1. Okay. All right, cool. So let me just delete all that stuff, and let's look into how many sigma bonds are present in this molecule. Okay. So what we need to know, all single bonds are made up of what? Sigma bonds, yes. A double bond, does that mean a double bond is 2 sigma bonds? Nope. A double bond is made up of a sigma interaction and a pi interaction. And then finally, a triple bond is made up of a sigma and 2 pi interactions. So that means all of these single bonds, and so do not forget these carbon-hydrogen bonds, 1, 2, 3, 4. All of those single bonds are sigma interactions. So there's 4. But then how many additional sigma bonds are there? There's 2 more. So there's two double bonds where the first component is a sigma interaction, and then the second component is a pi interaction. So there are 6 sigma bonds and 2 pi bonds in that molecule. I know it didn't ask it, but there's 2 pi bonds. All right, and that takes care of all of the bonding in that molecule. And that's useful for this next question. How many total unhybridized p orbitals are required to form this molecule? So how do you make a pi interaction? What makes it different? What makes it different? So sigma interactions are what kind of interactions? Head-on overlap, like 2 s orbitals colliding with one another to make this kind of overlap. 2 p orbitals can make a sigma bond like this if they're head-on, right? Those are all sigma interactions. But a pi interaction is different. It's a little bit weaker. It's not head-on overlap. It's actually side-by-side overlap between what 2 kinds of orbitals? P orbitals, yeah, but they have to be p orbitals that are parallel to one another. So this is a sigma interaction between 2 p orbitals head-on like this, but a pi interaction, it looks like this, where the overlap is side-by-side like this, right? Versus a sigma is this way, pi is this way. Right? So in both cases, both of these are made from p orbitals, but the orientations are different. Okay. So then the question is, how many total unhybridized p orbitals are required to form this entire molecule? There's actually 2 ways to do this. The easy way, or I don't know, yeah, the easy way is recognize, oh, this molecule has 2 pi interactions. In order to make a pi interaction, you need how many p orbitals? 2. So therefore, to make 2 pi interactions, you need 4. Yeah, so, 2 pi's times 2 p orbitals each, there's 4 p orbitals total. Unhybridized p orbitals. Here's another way to do it, because I just want to show you that everything kind of comes together. Let's look at the hybridized. So note here, the question is how many unhybridized p orbitals? So remember when we hybridize things, we'd have an s orbital, we have 3 p orbitals, and so hybridization is just we're saying, oh, if we have 3 electron domains, we only need to mix 3 of the atomic orbitals, leaving this unhybridized p orbital left over. So if we look at sp2 hybrids, how many leftover p orbitals are on this carbon atom right here? If it's sp2 hybrids, sp2 hybrid, how many leftover p orbitals did I not put in that blender when I hybridized everything? There's 1 left over. But what about if I sp hybridized it? I only had to mix 2 atomic orbitals. So in this middle carbon, how many leftover p orbitals did I not touch? 1, 2. So there's 2. And then this last carbon, how many unhybridized p orbitals did I leave untouched in an sp2 hybrid? 1. And that adds up to 4. The same 4 that we got from 4 p orbitals required to make 2 pi interactions. So all of this comes together, that when you hybridize something, it's the leftover p orbitals that are able to make pi interactions as long as there's unpaired electrons in there. All right. Okay, so that's 20. I like 20. So let's do 21. I like 21 as well. Okay, so let's look at this. So here, it's also valence bond theory, and I think valence bond theory is one of the hardest advanced theories, because we have to think about unpaired electrons. They exist in orbitals. They have to overlap in space to form sigma or pi bonds. So I give you the valence bond picture here, and I'm asking you which atom represents this. It would be a much easier question if I just asked you, what's the hybridization of this carbon? What would you say? sp3, right? What's the hybridization of this carbon? sp2, yeah. Or this oxygen, what's the hybridization of that oxygen? sp, what do we think? How many electron domains? 3. So 1, 2, 3. So this is sp2. Yeah. This oxygen also has 2 lone pairs on it and a single bond to that hydrogen. What's the hybridization of that oxygen? sp3, sp3. Yeah. So in that type of question, it's a lot more straightforward, but to add an element of difficulty here, I give you a valence bond picture, and I'm asking you to kind of do it backwards. I'm asking you, okay, which atom represents this hybridization? There's actually a ton of information we can get from this valence bond picture. I guess the first thing is, okay, I give you like an sp2 set, and then we have this unhybridized p orbital. Do we actually care about this 1s orbital? No. Why? It's in the inner core. We only really care about valence electrons. It's only valence electrons that are involved in chemical bonding. All right? Okay, what other information can we unpack from this valence bond picture? sp2. What does sp2 tell me about the atom? That it has, how do we know something's sp2 hybrid? Has 3 electron domains. So this is telling me that the atom that I'm trying to choose needs 3 electron domains. And then what does this unpaired electron in a p orbital, what does that tell me? That this atom also has a unhybridized p orbitals. They make what kind of bond? It has a pi interaction. So this valence bond picture is telling me that the atom I care about, that I want to choose, has 3 electron domains and it has a double bond in it somewhere. All right. Also, there's one more piece of information we can get from that valence bond picture, and it's based upon the number of electrons that are there. Yeah, that is. So how many unpaired or how many total electrons are in the valence shell? 4. So what atom is it? What element is it probably? What elements have 4 valence electrons? Carbon. Yeah, so this is probably a carbon atom. So we already eliminated half of these options, right? That we can eliminate. Oh, it's not the oxygen atoms. It has to be this carbon or this carbon. Which one is it? Is it carbon 1 or 2? It's carbon 2. Yes, it's carbon 2. What would if it was carbon 1, what would the valence bond picture look like? If it was carbon 1, it would have to be sp3 hybrid, and the 4 valence electrons would all be unpaired like this. Where this indicates to me, oh, this molecule or this atom makes 1, 2, 3, 4 sigma bonds with other things. That's this carbon, because it has 1, 2, 3, 4 sigma bonds, single bonds to it. But this carbon only has 3 sigma bonds, so 1, 2, 3, and then a pi interaction also to that oxygen. And so that's why the answer is carbon number 2. All right. Good. Okay. Okay. All right. So, then let's do this one too. I like this one. Let's look at this molecule, an interaction between A and A. So, what kind of bonding interaction is this? Where's the bond? It's between the 2 A atoms. So what kind of overlap is that? Sigma, yes, sigma. It's not pi. And so since this is valence bond theory, the phasing is right. We're not going to pick pi star. That's not pi star. Okay, what is the hybridization of each of the A atoms? So we just want to look at one of the A atoms, and the shape of the lobes on the outside should be able to tell us what the hybridization is. So what do we think? This A atom, it looks like it has how many electron domains? If all of these lobes are electrons. Has 3 electron domains, and what hybridization do we call that? sp2. Cool. And so then the last one, can ethane, is this ethane depicted? So maybe if we draw ethane, which is 2 carbon atoms bonded. Each of those carbon atoms have 3 hydrogens attached to it. So, can ethane adopt this picture? No, why? What's the giveaway? That carbon has to be sp2 hybrid. Is this carbon sp2? Nope, it is sp3. So in this case, no, it can't. All right, how do I know that this carbon's sp3 hybridized? This one right here? Has 4 electron domains. There's 4 bonds to it. So this ethane cannot adopt this picture. Okay, cool. Cool. What would so this shape around this A atom looks like which one of our Vesper theory shapes? Trigonal planar. The carbon in ethane has what geometry? Tetrahedral, yeah. And so we see that those two do not template on each other, right? So that means the 2 electrons, or the orbitals that make up this chemical bond between carbon and carbon, is an sp3 hybrid on one carbon and an sp3 carbon on another carbon. So that's what makes the chemical bond between those 2 carbons. But in this picture, that bond is made up of an sp2 hybrid interacting with an sp2 hybrid. But yes, in ethane, it's an sp3 interacting with an sp3, because that's the hybridization of those adjacent carbon atoms. Okay. All right, let's keep going. Okay, how many total sigma bonds are present in this molecule? Sigma. So remember, you just have to know, single bonds are sigma bonds. Double bonds are made up of a sigma and pi. A triple bond is a sigma, pi, and pi. So basically, we're counting the first component. Sigma is the first component in every bond. So I'll just count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's all the single bonds. But then we have some multiple bonds here, where only the first component is sigma. So how many is that? I lost count. 13? 13? Okay. All right. And then how many pi bonds? So we're counting the second component of the double bond. And then in the triple bond, how many pi components are there? 2. So then there are 3 pi bonds. Okay. What is the hybridization of the carbon and nitrogen that interact to make up the C-N triple bond? So I think if you just look at the structure, it's asking what is the hybridization of that nitrogen and that carbon. So the nitrogen has how many domains? 2. So it is what hybridization? sp. Carbon has how many domains? 2. So it is sp. Cool. What if I asked you, so how many pi interactions are in this triple bond? 2. What if I asked you, how many unhybridized p orbitals do you need to make that triple bond? Unhybridized p orbitals. 4, yeah, because 2 p orbitals interact to make a pi bond. All right, so let's think about the hybridizations of the carbon and nitrogen. So if I'm sp hybridized, so I'm taking like an s orbital and then I have p orbitals, but I'm only mixing 2 of them. I'm only mixing 2 of them. How many leftover p orbitals do I have after I hybridize to sp? I only have 2, so the new picture looks like this. There's my sp hybrid, there are my unhybridized p orbitals. So since nitrogen and carbon are sp hybridized, so this is nitrogen, that's carbon, there's my sp set, there's my unhybridized p orbitals. All right? For each of those, so you can see, oh, there's 1, 2, 3, 4 unhybridized p orbitals on each of those atoms. So let's actually fill in the electrons. So 1, 2, 3, 4, 5 on nitrogen, 1, 2, 3, 4 on carbon. So remember, I said that 2 unhybridized p orbitals, they interact to form a pi bond. So there is 1 pi bond, there is the other pi bond. Does that make sense in terms of what type of bond is being formed here. It's a triple bond. A triple bond has 2 pi interactions. How many pi interactions did I make here? 2. I made 2. What is this interaction that's happening right there? Right there. That's the sigma interaction. Does a triple bond have a sigma bond in it? Yes, it does. Yes, it does. What is that? Does this orbital interact to make a bond on nitrogen? No. What is that? That is the lone pair on nitrogen. Right there. So here, let me highlight that. There's the lone pair on nitrogen. And then the last electron we didn't account for, it's this electron right here on carbon. What's this electron doing? It's making a sigma bond, but a sigma bond with what? The carbon on the other side. Yeah, so here is one sigma bond with nitrogen, and then this carbon has another sigma bond with the carbon that's next door. All right, and that's how we inventory every single electron in this valence bond picture. Okay. All right, did we answer all the questions? No. What is the hybridization of carbon and oxygen? So these two. What are the hybridizations of those? sp2. Cool. So between carbon and oxygen, there's how many pi interactions? 1. So then how many unhybridized p orbitals are between carbon and oxygen? 2. Yep, because 1 pi interaction requires 2 unhybridized p orbitals. Okay, and then finally, how many atoms are sp3 hybridized in this entire molecule? So if we are looking for sp3 hybridized, what are we actually looking for in the molecule? For not necessarily 4 bonds, but 4 electron domains. 4 electron domains. So that's what we're looking for here. So how many? This carbon has 4 bonds. This one has 4 bonds. This one has 4 bonds. So yes, we ended up having ones with 4 bonds. But let me just say, if this bond was like a nitrogen, it had a lone pair and then 3 hydrogens, if that's what the molecule was, then this nitrogen is also sp3 hybridized. If there's a lone pair and 3 bonds, because the whole idea here is we just need 4 electron domains. An electron domain can be in the form of a bond or a lone pair. Okay. We're making our way down to 24 or 25. Okay, so that's 23. Okay. So we did valence bond theory, and then the very last advanced theory of chemical bonding with molecular compounds is MO theory, which stands for molecular orbital theory. So we need to consider the idea that electrons, they not only exist in orbitals, but electrons are also waves. And so waves can add up. They can add constructively, or they can add up destructively, like that, where they destroy one another. So we already talked about sigma and pi bonds in terms of valence bond theory, but now with MO theory, we are now considering, for every sigma interaction, for every head-on overlap we have a sigma interaction, which is a stabilizing factor, but we also have a sigma star molecular orbital where the waves, the electrons, which are waves, add up deconstructively and make a bond-destroying molecular orbital. So same thing with pi. When p orbitals come together to make pi interactions, they can do so constructively to make a pi bonding orbital, but we can also have a pi star, which is deconstructive. So these antibonds typically have nodes present in their molecular orbitals. So if we look at these pictures, you can see, our atoms are these dots in the middle of these electron densities. So what you're looking at right now are molecular orbitals, which come from atomic orbitals interacting. So we need to ask ourselves, what kinds of atomic orbitals are interacting, and we need to ask ourselves, is it bonding or anti-bonding? And then finally, we need to ask ourselves, is it a pi interaction or a sigma interaction? So let's look at A real quick. So if we put electron density in these orbitals, are they bonding or anti-bonding? Does it strengthen the bond or does it weaken the bond? Here it weakens the bond, and the giveaway is this dotted line. This dotted line is a node, which typically corresponds to antibonds because we're not putting electron density between the atoms. Compare that to picture B. In picture B, do you see that all the electron density is between the atoms? So this is actually a bonding orbital. Right, that putting electron density between in this type of orbital in this space will actually strengthen the bond. Right, so this is a bonding orbital, while this is an anti-bonding orbital. So let's look at this one. So this bonding orbital was made from two different p orbitals interacting like this, right, overlapping like this. So if you like squint your eyes and think, okay, what atomic orbitals are the parents of this molecular orbital that we're looking at? The parents are two p orbitals overlapping this way. What is this kind of interaction? Is it pi or sigma? This would be sigma. So this B, which I think is probably the easiest one here, is a sigma interaction that's bonding, but it's between p orbitals. So if we look at this structure here, our spaghetti diagram, our MO diagram, these interactions are different from these interactions. So the bottom ones here, what atomic orbitals are combining? These are s orbitals. S orbitals combine to make a sigma and a sigma star. But these top atomic orbitals are what orbitals interacting? P. And so if we look at the placement here, the first line here is what kind of MO? Sigma, but between p orbitals. And then the double line here is what kind of interaction? Pi, and then the next one, pi star, and then sigma star. So where does spot B go? Does it go in the S or the P interactions? Goes in the P interactions. And then we ask ourselves, was it bonding or anti-bonding? Bonding, and then finally it's sigma. So we can say for certain that that interaction goes right there. Okay, what is interaction? What is MOC? This one. What kind of, is it bonding or anti? Anti, yeah, because we have that node that's present. Who are its atomic orbital parents? P orbitals. P orbitals are coming together to make this molecular orbital. So we're looking at these interactions on the top, not the s orbitals. So it's anti-bonding. Its parents are p orbitals. So finally, is it a sigma interaction or a pi interaction? Sigma. So which spot does it go in? 1, 2, or 3? The first one, yeah. So that is C. All right, that we were able to deduce that this is a sigma star between p orbitals. Okay, let's look at D. Who are its parents? S orbitals or p orbitals? P, yeah. So that means, are we going to look at the top ones or the bottom interactions? The top interactions, yeah. So this is between p orbitals. Is it bonding or anti-bonding? Anti-bonding, because the giveaway is the dotted line, but it's putting electron density away from the atoms themselves. That's bond destroying. And then finally, is it a pi or a sigma interaction? Pi, yeah. So we are looking for a pi star between p orbitals. But will you find pi interactions with s orbitals? No, you won't anyway. So D goes where? Here. Goes there. Okay. And then finally, let's go back to A. So what is it? Bonding or anti-bonding? Anti. Who are its parents? S orbitals. And then finally, is it sigma or pi interactions? Sigma. Well, will you find pi interactions with s orbitals? No, you won't. So this is s orbital, so it is sigma star within the s interactions. So it is not this top one, it's this, the bottom s interactions, but pi star, so that is A. All right, so it's interesting, both A and C, they're both they're both sigma star interactions, both of them. But one of them, its parents are s atomic orbitals, and in C, its parents are p atomic orbitals. We have two choices of sigma stars between p interactions or s interactions, so you need to make sure you pick the right one there. Okay, finally, let's do number 24. Or 25, okay. And it's which one possesses the strongest bond. So we know you're always given the MO diagrams, but it's just up to us to place the electrons. So based upon the series we're working with, do we want to work with this diagram, the first diagram, or the second diagram? The second, so we can just ignore this first one, all right? So just like when we made Lewis structures and we counted valence electrons. Oxygen, so if you were doing the 6 steps for Lewis structures and you did oxygen, diatomic oxygen, how many electrons would you place in the Lewis structure? 6 times 2, because there's 2 oxygens, so 12. So 12 electrons. So we're actually going to put 12 electrons in the molecular orbital as well, right? Each oxygen is contributing 6 valence electrons. So we're going to put 12 electrons in that central MO. And all we need to do is follow like Hund's rule and all those things. So, so remember, these are sigma, sigma star, sigma, pi, pi star, sigma star. So we place the 12 electrons following Hund's rule. So 1, 2, 3, 4, 5, 6, 7, 8. So see how I'm spreading out those pi electrons? 8, 9, 10, 11, 12. I didn't put the up-down arrows because it's not asking for like paramagnetism or anything. So I'm just, the electrons are just lines, right? Just pretend that they have spins. All right. So just like before, when a question asks for strongest bond, what does that actually mean? It means bond order. Yeah, so strongest bond means we are looking for the one with the highest bond order. So we can calculate the bond order from this MO diagram using a different kind of bond order calculation. And this one is specific for MO diagrams. We take the number of electrons in bonding orbitals. Because bonding orbitals strengthen bonds. But electrons in anti-bonding orbitals weaken bonds. So we want to subtract electrons in anti-bonding orbitals. Whoops, sorry. Where did I go? Anti-bonding orbitals. And then we want to divide by 2, and that's it. So we just need to count how many electrons are in bonding orbitals, how many are in anti-bonding orbitals, and then divide by 2. All right, and so you can note here, so this molecule that we just did right here is just neutral diatomic oxygen. If you draw the Lewis structure for oxygen, it looks like this. There's a double bond. So what do you think when we calculate the bond order of O2 using the MO diagram? What do you think we'll calculate a bond order of if the Lewis structure has a double bond? We should probably calculate a bond order of 2. So let's check it. So if we calculate this, there are 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals. How many electrons are in anti-bonding orbitals? 1, 2, 3, 4. So 8 minus 4 over 2 equals 2. So does the MO diagram agree with the Lewis structure in terms of bond order? Yes, the Lewis structure has a double bond. MO theory says it also has a double bond. And that's how advanced theory should be. They should always agree with all the other supporting theories. All right, so that's O2. Neutral. What do you think we have to do to make O2 plus? It's a cation. What do you think we do? We take away an electron, but which electron do we take away? Which one? The topmost one, yeah. So to make O2 cation, we just remove an electron. But be specific, which electron did we remove? What kind of MO did we take it from? A antibonding orbital. So now for O2 minus, or sorry, plus, the bond order calculation, it's 8 minus 3, because we removed an antibonding orbital. So removing an electron from an antibonding orbital will actually strengthen the bond, because now the bond order is what? 2.5. Yes, 2.5. So let's do O2 minus. So to do O2 minus, again, start with the neutral molecule. So I'll go back to the O neutral one. So to make an anion, what do you think we have to do? Add an electron, but we're adding an electron where? To a pi star, so an antibonding orbital. So now, when you calculate bond order, it's 8 minus 5 over 2. So we see that the bond order is 1.5. So the idea here is start with the neutral molecule. If you're working with a cation or anion, just remove or add to the topmost positions and calculate the new bond order. And so there's a question here about para or diamagnetism. Yeah, so this question could easily be asked about para or diamagnetism. So if we go back to this diagram, so I don't actually have spins present, but if we look at neutral oxygen with 2 unpaired electrons in its pi star, we see that the presence of unpaired electrons makes diatomic oxygen paramagnetic. But if we wanted to look at like diatomic fluorine, where we have to add 2 more electrons, we see that diatomic fluorine is actually diamagnetic because everything's paired up, right? Okay, so that's it. For the questions we didn't do, feel free to look at the key. Best of luck.